Hi, welcome back. Second last lecture today is on artificial intelligence. This is an important topic because it's playing an increasingly important role, not just in marketing and in business, but in many different domains of society, affecting consumer behavior in a lot of different ways. So it's important for anyone in any field to understand what AI is, what it's doing, where it's going, and some of the big issues it's bringing up, both for society and for business. So we'll start off the lecture looking at a definition of AI, trying to understand it from a couple of different angles because it's quite a complex and kind of vague term. So we'll dive into what people really mean when they talk about AI. Then we'll talk about three of these big social issues that AI is really bringing up. So the first is what's called the black box, which is the notion that often AI is uninterpretable. So it will arrive at decisions or suggestions or predictions without humans being able to interpret how it arrived at that outcome. And that will bring up some really big challenges. So we'll look at this issue of AI being a black box. Then we'll look at the concept of machine bias. So this is the idea that AI can often entrench and formalize biases that humans have in areas like racism, for example. And then we'll talk about the impact that AI is likely to have on the labor market, so on creating or destroying jobs, and some of the big questions in that area. Then we'll talk a little bit about some recent research in marketing as well as other closely related fields on a concept called algorithm aversion, which is basically the idea that humans often prefer to rely on humans rather than algorithms, so they're averse to relying on algorithms, even when the algorithms can perform much better than humans can. And then finally, we'll wrap up with a quick discussion of how AI is really big business these days, and especially in Edmonton. Edmonton is actually a world leader in both the basic research as well as the commercialization of AI. So we'll look at that. So a lot of different experts have different specific definitions for what AI is, but I think this is a good recent one. So any kind of machine that uses any kind of algorithm or statistical model, so you can think about algorithm and statistical model as synonyms, to perform perceptual, cognitive, and conversational functions typical of the human mind. So things like visual and speech recognition, reasoning, problem solving. You could put it more simply as thinking about a machine or a computer doing any task that we typically think of as intelligent. It's a bit of a tricky definition because often the goalposts change. So back in the 50s and 60s, people were thinking that if a computer could beat a chess grandmaster, that would be artificial intelligence because chess requires intelligence. But as that landmark was reached and computers started to beat humans in chess, people started to say, okay, well, chess, that's not really intelligence, that's just computation. So now let's shift it. Maybe, let's say, if a computer can play the game of Go at a really high level, that would truly be AI. That happened recently too, and you see this continual process of the goalposts kind of shifting for what counts as intelligence. So it's tricky to define exactly what it is, what intelligence is, what artificial intelligence is. So instead of trying to come up with this comprehensive definition, we'll look at specific sub-technologies that make up the field of AI and look at how those technologies work and what they do. Before we do that, there's an important distinction between artificial general intelligence and artificial narrow intelligence. So AGI, this is a hypothetical form of AI that does not currently exist. This is a form of AI that would have human-level intelligence in every sense. So it would be able to walk around, pick up objects, do math, learn history, sing, write music. Basically, it would have all of the same intellectual capabilities as humans do. So this is a very ambitious goal that some companies are working on trying to achieve. Some people think it's very dangerous as a goal to create this kind of human-level general intelligence. And the reading for this lecture will go into some of that debate. But for now, all of the existing forms of AI that we have are artificial narrow intelligences, which just means that they're narrowly focused on accomplishing one task or a set of related tasks. And they can be really good at those tasks, but completely useless at other tasks. So for example, driverless cars, it's a form of AI. They're very good at driving cars, but they can't catch a football or cook a meal, for example. Other forms of simpler AI would be, for example, Siri on the iPhone or Alexa. They're very good at speech recognition and speech production, but completely useless at playing chess, for example. Another really basic concept to become familiar with before moving on to talking about AI more is the concept of an algorithm. So this is pretty straightforward. It's basically an algorithm is a set of steps that a computer can follow to perform a task. So a really basic algorithm could be used to find the average of a set of numbers, right? Everybody learned this in grade school or high school. You sum up all of the numbers and divide by the number of numbers. So that formula is a very basic algorithm that a computer could use this, follow these steps, and compute the average of a set of numbers. Another example of a pretty simple algorithm, this was one used to predict how likely somebody would be to miss their court date. So it could be used, for example, in deciding whether or not to give someone, to grant someone bail, to release them on bail. And it basically looks at two factors, so the defendant's age, so what age range they fall into, you give them a score based on that age range, and then how many past court dates they've missed, you give them a score based on that. You just add these two numbers up, and that gives you this flight risk, so how likely they are to miss their future court date. So that's a simple algorithm as well. Give them a score based on age, give them a score based on past court dates missed, add them up, that's the flight risk. So these are two very simple algorithms. The kinds of algorithms that artificial intelligence uses are a lot more complex than that, but the basic concept is the same. It's the set of steps that a computer follows to perform a task. So algorithms really do underlie all forms of artificial intelligence. Okay, so I mentioned a couple of minutes ago that it's more useful to look at the specific concrete technologies that make up AI rather than trying to come up with this perfect grand definition of AI. So these are really the major subfields of AI research. So if you look at an AI textbook, it will often be broken down into categories like this as different subfields of AI. So first, and probably most important, is machine learning. You've probably heard this term before. Machine learning really does underlie a lot of these other subfields of AI. And machine learning refers to a set of algorithms that can learn the best inputs on its own rather than having the inputs coded by humans. So for example, if you go back to this example of a flight risk algorithm, here this is a case where humans chose age and past court dates missed as the inputs to predict the output flight risk. Whereas a machine learning algorithm, the algorithm would choose these inputs on its own. It would learn what the best inputs are, what the best predictors are, based on analyzing a huge amount of data. So it would look for patterns on its own between a whole bunch of different inputs and the output that you're interested in, and the algorithm, would choose what the best inputs are. So the predictor variables are learned automatically rather than being chosen by a human. So that's a key feature of machine learning algorithms. And then deep learning you might have heard of as well. It's a subfield of machine learning where you have much more complex relationships between the inputs and outputs, and each of those relationships is learned automatically by the algorithm. Then a second subfield of AI is called knowledge representation and reasoning. So this is about how computers store and use information. Another example would be driverless cars need to have a basic understanding of how physics works, how pedestrians usually behave, how to categorize things into pedestrians or other kinds of obstacles, for example. So artificial intelligence often has to have these forms of knowledge encoded formally so that it can be useful. So this is another subfield where people are working on how machines can best represent knowledge and use that knowledge in the service of reasoning. Third subfield is natural language processing. So this is the form of AI that underlies Siri and Alexa. It allows them to understand the words you're speaking to them and then generate speech on their own. And natural language processing often does rely on machine learning and deep learning to break language down into its constituent components. So for example, looking at the specific sounds or syllables that come in and predicting what words those sounds or syllables make up. So that's another important subfield of AI. Fourth is computer vision. So again, a whole field of researchers working on how to give computers the ability to see the world around it. So using inputs like cameras, as well as radar detectors, LiDAR detectors, and then robotics. So this is basically physically embodied forms of AI. And you can break the field of robotics itself down into different categories. So you have manipulator robots, which are basically like stationary arms in a factory, mobile robots like drones and self-driving cars, and then humanoid robots that have a human-like body and can walk around and manipulate the environment. So the point of this slide is just to emphasize that the field of AI is huge and complex, and when you hear people talking about AI, they could be talking about any of these different subfields. So in general, it's good to get more specific and more concrete when you're talking about AI or hearing about AI, questioning what exactly they're talking about. Is it the ability to see the world around them? Is it the ability for machines to generate speech? Is it physical robots? And so on. So we'll focus a little more in depth on machine learning. This is really one of the most important subfields of AI. It often underlies a lot of the other subfields. And it's because of success in machine learning research that AI has really exploded in terms of how influential and how important it is in the last few decades. All right, so we've already seen that machine learning algorithms can essentially learn what the best inputs are without being pre-programmed. So learning what the best inputs are in terms of predicting an output. So we'll look at an example of how this works. So the first step of building a machine learning algorithm is what's called the training phase. So it's where the algorithm is trained on a huge set of data that allows the algorithm to learn patterns. So for example, if you wanted to use machine learning to recognize pictures of cats, the training phase would involve gathering hundreds of thousands or millions of pictures and having humans label those pictures as either containing a cat or not containing a cat. And you give each of these labeled pictures to the algorithm. These pictures are called the training data, and then the algorithm tries to pick up on patterns that distinguish pictures of cats from pictures of non-cats. So in the training data, the key output that you're looking for, cat or not cat, in this case, is labeled by humans, but the algorithm itself is then trying to distinguish what the specific inputs are that are the best predictors of that output, cat or not cat. So looking for specific patterns among the millions of pictures that best distinguish between cats and non-cats. And then after the training phase, you have the prediction phase. So this is when the algorithm takes the patterns that it's identified in the training phase and tries to predict whether a cat is present in a new set of pictures that is unlabeled. So again, the training data was labeled by humans as containing cat or not cat. In the prediction phase, the algorithm is given unlabeled pictures, so it doesn't know whether there's a cat or not a cat in the pictures, and it uses the patterns it learned in the training phase, applies those patterns to the new pictures, and makes a prediction about whether a given picture contains a cat or not. So this is just a super basic, high-level description of how machine learning works. The key points are that there's first a training phase, where you have training data labeled by humans in terms of whether it has the output or not that you're interested in. So it could be cat or not cat, it could be spam email or not spam email. It could really be any kind of output that you're interested in. The algorithm automatically learns patterns between all of the possible inputs and that output that's been labeled by humans. And then in the prediction phase, it applies those patterns that it's learned to make predictions on unlabeled data. So if you want to use a machine learning algorithm, you have to first start with a huge set of labeled data so that the algorithm can learn patterns and then apply them to unlabeled data. Okay, so that's a brief high-level overview of what AI is and some of its key subfields. Now we'll look at some of the key social issues that AI is bringing to the fore. starting with this idea of AI being a black box. So because these algorithms that underlie AI are often extremely complicated, it's often not clear why an AI system made a given decision or a prediction. So the process by which the algorithm transforms inputs into outputs is so complex and has so many steps that sometimes even the programmers of the algorithm themselves can't fully explain how the algorithm got from the inputs to the outputs. And this can be highly problematic when algorithms are used for tasks like determining whether somebody should get parole or how harsh of a sentence a criminal defendant should receive. So often these machine learning algorithms are used in cases like this in the criminal justice system or in the healthcare system, for example, trying to make diagnoses or suggesting treatment options. Often algorithms can do tasks in these areas very effectively, but because the algorithms are so complex, the lawyers or the defendants or the patients or the doctors involved can't get satisfactory explanations for why the algorithm arrived at the conclusion that it has. So there's been an increasing movement towards what's called interpretable AI, so trying to build algorithms that are actually interpretable to human beings. But some people worry that the more interpretable you make the algorithm, the simpler it will have to be, so therefore the less effective it will be. So there's an idea that's called the accuracy interpretability trade-off. So basically, the more accurate the algorithm is, the less interpretable it will be, because it's more complex, it has more steps. Whereas the more interpretable you make an algorithm, the less accurate it will be. However, it actually seems to be the case that this trade-off is probably overstated. So there's actually research comparing very complex algorithms to simpler ones and showing that sometimes the simpler ones can actually perform as well, as accurately as the more complex ones. So getting back to the criminal justice context, the most widely used algorithm for sentencing and parole decisions in the US is called the COMPAS model, which uses about 130 inputs. It's very widely used in the US criminal justice system. And it's a proprietary algorithm where the specific steps that it uses to transform these 130 inputs into an output of a parole decision is unknown. The company holds that as a trade secret, doesn't tell anybody specifically how the algorithm works. But research has actually shown that this 130-factor algorithm is actually no more effective than this very simple 3-factor algorithm, based on just age, gender, and the number of prior offenses. So in this case, and many others, these simpler algorithms can be just as effective as much more complex but less interpretable algorithms. Unfortunately, as I alluded to a minute ago, corporations who own the algorithms and sell them often have strong financial incentives to keep them uninterpretable. Because if they revealed how exactly their algorithms work, even if they're even able to, that would destroy their intellectual property advantage, their competitive advantage, and then they wouldn't be able to sell their algorithm for a profit. So because of this profit motive, it seems likely that the best approach to making algorithms more interpretable, opening up this black box, is through government regulation. And you're starting to see this, especially in the European Union. So their GDPR rule that came out a couple of years ago now and was really revolutionary actually requires tech companies to provide meaningful information about the logic involved in automated decisions about consumers, which essentially amounts to saying you have to be able to explain why algorithms made the decisions that they made when they're affecting consumers. So it's still kind of vague language in this new law. It stops short of requiring algorithms to be fully interpretable. Exactly what meaningful information constitutes is not exactly clear, but this is a step towards trying to make algorithms and AI more interpretable to the people who it affects. A second big issue, social issue around AI is the concept of machine bias. So the idea that the algorithms themselves can often contain the same kind of biases that humans do. So ProPublica, this is a really good investigative journalism website. They did an analysis of this algorithm used to grant parole decisions that we discussed a few minutes ago, this COMPAS model. And they found that essentially this algorithm was strongly biased against black defendants. So African Americans were about twice as likely than whites to be labeled as higher risk of reoffending, but then not to do so, not to reoffend. Whereas whites were almost twice as likely as blacks to be labeled as lower risk, but then to end up reoffending. So you could look at this as essentially the algorithm discriminating against African Americans. So ProPublica did an analysis of the algorithm and tried to understand why this might be. And they found that the algorithm didn't actually consider race as a factor, but it considered factors that were related to race. So questions like, have one of your parents ever been in jail? Did you get into fights at school? So questions like this that are indeed correlated to race, but that are correlated because of historic patterns of discrimination. So because American and Canadian society has always had systematic discrimination against visible minorities, that's resulted in disproportionate and unfair numbers of minorities ending up in the criminal justice system. And that's reflected in the training data, essentially, that the algorithm is using to relate the inputs to the outputs. So because the data that the algorithm was trained on reflects these human prejudices, this human discrimination, the algorithm has then essentially internalized and formalized those same biases. So we'll look at another example of machine bias in a different context, this time in facial recognition. So we'll watch a quick video explaining this concept.
That these systems can have some worrying blind spots, as one MIT researcher found out when testing out numerous algorithms, including Amazon's own recognition system.
At first glance, MIT researcher Joy Buolamwini says the overall accuracy rate was high, even though all companies better detected and identified men's faces than women's. But the error rate grew as she dug deeper.
Lighter male faces were the easiest to guess the gender on, and darker female faces were the hardest.
One system couldn't even detect if she had a face, and the others misidentified her gender. White guy, no problem.
Yeah, white guy, no problem, which, yes, is the unofficial motto of history. But it's not like what we needed right now was for computers to somehow find a way to exacerbate the problem. Now, on the one hand, these technical issues could get smoothed out over time. But even if this technology eventually becomes perfect, we should really be asking ourselves how much we're comfortable with it being used by police, by governments, by companies, or indeed by anyone.
Okay, so that's another example of how algorithms and AI can perpetuate and sometimes even exacerbate human bias and discrimination. All right, the last big issue we'll look at in terms of AI in society is in terms of automation and employment. AI is clearly threatening to disrupt a lot of different jobs and professions. So in the US, for example, the most popular job for males is truck driver. And you see now self-driving cars and trucks being just on the verge of widespread commercialization. So that's one example of AI threatening to put millions of American workers out of a job. Again, it's the most popular job for American males. It's not only blue-collar jobs like truck driver, though. You see AI being used to actually perform tasks like diagnosing skin cancers. So in 2017, a deep learning model, this is a machine learning algorithm essentially, was shown to actually perform these kinds of diagnoses with the same level of accuracy as human dermatologists, human doctors. So increasingly, even these white-collar professions seem to be threatened. You also see AI starting to perform more creative tasks, like creating art. So this was painting created entirely by AI that sold for about $400,000 at an auction last year. And then even more subjective tasks, like detecting what emotion is in someone's voice. AI can perform this particular task at the same level or higher, more accurately than humans can. So increasingly across all sorts of different tasks, jobs, and professions, AI is performing at human levels, which has a lot of people really worried about what its impact will be on the labor market. Okay, so if you look at the popular media and what they're talking about in terms of AI's impact on jobs, you'll actually see two really distinct narratives. So the first up top is that AI will enhance human workers, make it easier for us to do our jobs more effectively, that we'll really be able to collaborate, and that AI will complement human workers. Whereas on the other hand, you have people saying, actually no, robots and AI are going to completely steal our jobs, it's going to destroy all the human jobs, there will be mass unemployment. So which narrative ends up being closer to the truth is still very much unknown. It seems likely that some jobs will be entirely automated, probably jobs like truck driver, cashier, these sort of very repetitive jobs that don't take much creative or critical thinking. Whereas other jobs, like being a doctor, being a lawyer, they'll likely change significantly, where a big chunk of those jobs will be automated or outsourced to machines that can perform at human levels, whereas the humans will be left to perform some of the other aspects of that job. So I've recently done a little bit of research looking at how students and workers perceive this question of AI essentially being more of a helper to human workers or more of a competitor or a threat. So what we find when we ask a representative sample of American or Canadian workers whether they perceive AI as more of a helper, more of a competitor, if you just ask them about AI without specifying its performance level, so without telling them how well it performs compared to humans, most people see it as more of a helper, so this red curve here. But when you actually tell people that AI can perform many tasks as well as humans, so at very high levels, then people shift their perceptions and start to see it as more of a competitor. And you see the same kind of pattern when you ask people if AI is present or available in a specific field of work, would it make a job in that field more or less attractive to you? So when you ask them about an AI without specifying its performance level, it seems like people are more drawn to a job in that field where AI is available. Whereas when you inform them that actually AI can perform at human-like levels, they start to see jobs in that field as much less attractive. And then a similar pattern for when you ask people how likely they would be to use an AI tool themselves at work. They're quite likely to use it when they don't realize how effective it is, but when people realize that actually it performs as well as humans can, they become much less likely to say they'll use it. So it suggests that people often underestimate or don't realize how effective AI is. So when you just hear about AI being used, people might initially infer that, okay, it'll be a helper to human workers, it will be a great tool to have. But when people realize that, in fact, AI is really performing at human levels in a lot of fields, it makes it seem like much more of a competitor, much more of a threat. So this is worth keeping in mind and thinking more about as you're thinking about your own career path. So some fields, like accounting, for example, are starting to see a lot of automation already. So do your research, look into how AI is being used in the fields you're considering pursuing, and think about how it might be more of a helper to you in that field, in that career, or more of a competitor. Okay, now we'll talk a little bit about this idea of algorithm aversion. So there's quite a bit of research now showing that people tend to prefer to rely on humans rather than algorithms to perform the same task. even when algorithms can perform better. So these are just 3 quick examples from recent research. So the first here compared people's preferences for for hiring employees, either through thorough discussion with the candidates or through mathematical formulas like algorithms. And this research found that these thorough discussions, so human-based methods of evaluating employees, were viewed as more useful, more fair, and more flexible than using algorithms. When in fact there's a lot of research showing that interviews and discussions with job candidates is not useful at all. It's not a good predictor of employee success, whereas using simple algorithms is almost always a superior method. And just to highlight how powerful this algorithm aversion is in this case, even the psychologists, these researchers who have shown that algorithms outperform interviews, even those psychologists will continue to use interviews themselves when they're hiring new job candidates. Another example of algorithm aversion looked at people's perceptions of doctors who make an unaided diagnosis versus getting advice or help from a human colleague or from an algorithm. And these researchers found that doctors who get advice from an algorithm for a computer are perceived as having less ability, being less professional, and being less thorough compared to doctors who seek out advice from a human colleague, which again goes against recent evidence showing that algorithms often can perform at or above human levels at making diagnoses in medical contexts. And the last example here, although there are many more, is that looking at people's willingness to receive medical treatment themselves from either an algorithm or a human, researchers found that people much preferred to get all sorts of medical treatments from a human because they think that AI or algorithms neglect their own unique characteristics. So this idea that I'm a very unique individual, only a human can appreciate that, seems to be a strong factor in driving this algorithm aversion. So some researchers have started to look at how you can overcome algorithm aversion, because like we've seen, algorithms can often outperform humans. So sometimes there's really good reason to encourage people to use algorithms to overcome this algorithm aversion. So in one paper on this topic, researchers were asking people to use these inputs to predict how well high school students would perform on standardized tests. So the inputs were things like their race, their socioeconomic status, what region of the country they live in, and so on. And the researchers gave people the choice between making these predictions themselves or relying entirely on the predictions of an algorithm. So in the control condition, less than half of people chose to rely on the algorithm. Most people preferred to make the decisions themselves, the predictions themselves. But if you gave people the opportunity to adjust the algorithm's output, that significantly increased the number of people who were willing to use it. Okay, last quick section we'll talk about is in terms of the business impact of AI, especially in Edmonton. So this is just looking at AI's potential economic impact across different industries. And you'll see that across about a dozen industries here, the expected or potential impact of AI exceeds $100 billion. And across these 19 industries, there's potential for $3.5 to $5.8 trillion of economic impact annually. The growth rate is also extremely high, triple digits consistently over the past several years and into the next several years, up to 150% year-over-year growth in terms of the economic impact that AI has across industries. And Edmonton in particular is really a world leader, both in terms of basic research and commercialization of AI. So in terms of AI and machine learning research at universities, University of Alberta is ranked #2 in the world after only Carnegie Mellon, ahead of MIT, Cornell, Tsinghua. So the computer science department at the U of A is extremely well regarded. And outside of the university as well, you see a lot of leaders in the commercialization of AI in Edmonton as well. So Alta ML, short for Alberta Machine Learning, is a company started by Alberta School of Business alumni, Corey Jansen. And his company has been extremely successful and growing and hiring all the time, basically applying this AI research that's being done at the university to commercial contexts in a lot of different industries. There's a really good podcast you can listen to featuring Corey Jansen and some faculty at U of A talking about his company and how they're working to apply and commercialize AI. One of the most interesting and impressive recent developments in AI has also been based at the University of Alberta, and that's teaching AI how to play this ancient Chinese game of Go. So researchers at the university were key in building an AI system that beat the best human masters of this game, which was a remarkable achievement because Go is vastly more complicated than chess and often is thought to involve a lot more intuition and creativity than pretty much any other game. And the way these researchers built the program that became so successful at Go was quite remarkable. So we'll watch a quick video explaining a little bit of the background there.
AlphaGo has been through many generations now. The first generation of AlphaGo, which we published in our original Nature paper, was able to beat a professional player for the first time. Now we have the final version of AlphaGo, AlphaGo Zero, which has learned completely from scratch, from first principles, without using any human data, and has achieved the highest level of performance overall. The most important idea in AlphaGo Zero is that it learns completely tabula rasa. That means it starts completely from a blank slate and figures out for itself only from self-play and without any human knowledge, without any human data, without any human examples or features or intervention from humans. It discovers how to play the game of Go completely from first principles. So tabula rasa learning is extremely important to our goals and ambitions at DeepMind. And the reason is that if you can achieve tabula rasa learning, you really have an agent that can be transplanted from the game of Go to any other domain. You untie yourself from the specifics of the domain you're in and you come up with an algorithm which is so general that it can be applied anywhere. For us, the idea of AlphaGo is not to go out and defeat humans, but actually to discover what it means to do science and for a program to be able to learn for itself what knowledge is. So what we started to see was that AlphaGo Zero not only rediscovered the common patterns and openings that humans tend to play, these Joseki patterns that humans play in the corners, it also learned them, discovered them, and ultimately discarded them in preference for its own variants, which humans don't even know about or play at the moment. And so we can say that really what's happened is that in a short space of time, AlphaGo Zero has understood all of the Go knowledge that has been accumulated by humans over thousands of years of playing, and it's analysed it and it started to look at it and discover much of this knowledge for itself. And sometimes it's chosen to actually go beyond that and come up with something which the humans hadn't even discovered in this time period, and developed new pieces of knowledge which were creative and novel in many ways. We're all really excited by how far AlphaGo Zero has come, but I think what we're most excited about is how far it can go in the real world. That the fact that we've seen a program can achieve a very high level of performance in a domain as complicated and challenging as Go should mean that now we can start to tackle some of the most challenging and impactful problems for humanity.
So that company, DeepMind, that built this AlphaGo Zero, that company, people who started that company were trained at the University of Alberta. And DeepMind recently opened their first international office outside of London, England, right here in Edmonton. So if you are interested in becoming involved in AI from a business angle, from a business perspective, Edmonton is an excellent place to be to do that. And then the last point we'll wrap up on is thinking about the implications of this particular development, so AlphaGo Zero, for artificial general intelligence. So getting back to this distinction from earlier between narrow and general AI, what they seem to be building at DeepMind is an early form of artificial general intelligence. So the reading for this lecture, Wait But Why, goes into this a lot more detail, so I hope you'll read it. But here you see the median expert prediction for when we'll get an artificial general intelligence. Just 2040, just 20 years away, we could have this completely general human level artificial intelligence, which is quite remarkable. And then once you have a general intelligence, a lot of people believe that it will be able to quickly improve itself to eventually become an artificial superintelligence, meaning an AI that's superior to human level intelligence in every way. And there you have the median expert prediction for a superintelligence by the year 2060. So when you're talking about general or superintelligence, you completely change the discussion from everything we've talked about in this lecture. Some people think superintelligence would have unbelievably positive and beneficial effects, solving climate change, curing cancer, figuring out all of the most important problems facing society, whereas other people think a superintelligence could actually spell the end of humanity. So fascinating and important questions for sure, and worth reading the Wait But Why articles assigned for this lecture to learn more about it. All right, that's it. Last lecture next week on happiness. Until then, thanks for watching, and see you next time.